Hello all, today lesson we are going to have a look at transformations on tangent graph. You have the basic understanding of the graph of the tangent. We'll come back to this summary later. Let's have a look at these two examples that I'm going to discuss in sketching. The first one given as 5 tan 3x. I have given you the tan x graph here. So this is simply tan x graph. We have a dilation factor 3 here, or rather 1/3, and then here 5. So the number 5 means you are stretching away from the x-axis, and number 3 mean you are dilating from the y-axis. In this case, we have to rearrange the equation as y equals 5 tan x on 1/3. So the dilation factor is 1/3 here. What it means is you are squeezing the graph towards the y-axis. Simply the lengths here are getting 1/3 the normal length. What it means to us, we have the asymptote at pi on 2. Now it is 1/3 the pi on 2. In that case, we have, that's 90. When you divide that by 3, you would get 30 degrees, pi on 6. So you need to draw an asymptote across pi on 6. And there's another one. Where's the other one? One onto the left hand side is negative pi on 6, just in here. Now what has happened, I need to get it a little nicer. Okay, now we have squashed the graph by 1/3. So that's the shape. Now what's going to happen, this is going to repeat. So this is going to repeat every pi on 3. Now you can see the asymptote at pi on 6 and from negative pi on 6 in this case. Therefore the gap here, the period for this graph is pi on 6. Now if you look at here, it's tan nx form where n is 3 now. Therefore we would have the period as n is 3. We can write down period is pi on n, in this case pi on 3. Hence we have got that one using the graph itself. Now we have to repeat this. I need to carefully sketch all the 1/3 of 90 now, and then this one is in here, and I'm going to start my graph and repeat nicely onto the pi on 2, then again just here and there, where we have next asymptote 2/3 the way of this length. We have it here, right? And then we sketch again. Now you got to repeat, and then you stop here because that's where you're going to stop given the condition x is between negative pi to pi. And you repeat this to the left hand side, and we do exactly the same as we've been doing. Now this is negative pi on 6, that's negative pi on 3. Hence the graph looks like that. And then again we repeat until we hit negative pi. So we're going to break this into 3 bits and get the asymptote. And then sketch. You also can see the dilation factor 5, which is away from the x-axis, the one we had here, is applied onto this purple graph, which means you getting away from the x-axis faster than the normal tan graph. That cannot be explained here quite clearly with the sketching, but you can put a number and then you can get the height for this particular value for whatever radian that you're going to pick. Then you can calculate the height and then put that point on the graph, which is not necessary in this case. Now let's move on to the next graph, which is again reference 1 given as 10x. And we have tan 2x. Tan 2x is basically squeezing towards the y-axis. Again, y-axis. Then you get the asymptotes halfway through at negative pi on 4 and pi on 4. But you got to be careful here. There is a sign in the front negative. What it means for us is a reflection through the x-axis. So whenever you get the graph, you flip it. Normally, it's like that. Well, then if it is flipped, we should get the graph upside down or reflected through the x-axis. So if I did that, I should get a graph like this. And then what I'm going to do is I'm going to repeat that one for every period that I have. In this case, it's pi on 2 because tan 2x. The period is pi on 2. Let me move that a bit further away from the graph. Let's sketch. Here we have another one. Right. And then we keep doing until we hit pi. In this case, you gotta come down and then hit nicely that side, and then again into the left hand side. That's where the next asymptote is gonna happen. Let me quickly get that down. Then you have the graph like that, and then from here the graph like this, because you gotta start off from negative pi. The left hand side just in here, the one that comes down there, just in here, it's not going to appear because you're going to truncate at negative pi. And that's how you sketch the tan graph with dilations and reflections. Okay, now let's move on to solving equations. Well, the first one we've been given is tan x is 1. So the gradient 1. If I look at the unit circle, and if you remember the exact values from the table, the very first one that gives me the gradient 1 is 45 degrees, or rather pi on 4. Therefore you can write down x is pi on 4. Well, what else? Pi on 4. Let's have a look at here. Pi on 4. And of course, this is between negative pi to pi. Hence, what I'm looking at here is going further into the left anticlockwise until I hit pi. I don't find any other. But when you go forward, you will get exactly the same amount here, which is pi on 4. Therefore, pi minus pi on 4, 3 pi on 4, but that's negative. Hence, our two answers are negative 3 pi on 4, comma pi on 4 for this case. I'm going to consider this one, tan 3x equals negative 1. Now, we need to look at negative 1. I know that from symmetric property, we can, in fact, calculate that one easily. If I have the unit circle and if I know the gradient at pi on 4 is 1, that's tan pi on 4 is 1, then what is negative 1? Negative 1 occurs when this is pi on 4. In that case, the full angle here is 3 pi on 4. So very first value we get is 3 pi on 4. So let me write down that here. There is a reason. 3 pi on 4. Okay, that's good. Now, if that was x, see, I replaced the 3x with an x. Now, if that was x, let's say theta. If that was theta, theta should be 3 pi on 4. Now, if I go to the positive side, I'm going to write them in light blue. That's negative pi on 4. You hit negative 1 gradient. Therefore, the other one is negative pi on 4. Now, what we are looking at here is 3x, not just x. Hence, eventually what happens is we are going to divide the whole equation by 3. So what it means is, for us in the unit circle, you are going to squeeze the values, the angles in 3 revolutions, around 3 revolutions into 1. Therefore, we need to consider going around until we hit 3 revolutions, so that final answers are in negative pi to pi. So simply you're going backward till negative 3 pi to 3 pi. That means you go forward 1.5, backward 1.5 of this unit circle to find the answers for this case. Now let's go forward. In this case, anti-clockwise. Let's go anti-clockwise. I'm going to use my purple color. So what is the next one you get? When you come all the way, you hit this line again at that point, which is pi on 4 less 2 pi. So that's basically 2 pi minus pi on 4. So if you calculate that one, that will be 7 pi on 4. And then you go forward again, then you hit that value again, that's 2 pi. So you've done a 2 pi plus 3 pi on 4. So that's a 2 pi plus 3 pi on 4. So if you do the calculations, you will get 11 pi on 4. Now we're going to stop, because we're going to stop at 1.5 revolution anti-clockwise. Now let's go clockwise, 1.5 revolutions. The first one we got. The second one we're going to hit here. That will be negative pi. And then another negative pi on 4, making negative 5 pi on 4. And then you go a bit further until you hit that full revolution. That means negative 2 pi. And then again negative pi on 4. So that gives me negative 9 pi on 4. The reason I've written initial values down here, because I need more space to write down the rest. Now what I'm going to do is I'm going to divide both sides by 3 to find the proper values of x. Simply the denominator becomes 12. Therefore, answer is, either you can simplify these ones, negative 3 pi on 4, which I encourage if they cancel, negative 5 pi on 12, negative pi on 12, and then pi on 4, 7 pi on 12, and then 11 pi on 12. You can see we have not 2 as we seen before. Normally we get 2 solutions. Because it's 3, you're looking at 3 times many solutions I had for my normal case. That means 6 solutions. Okay, the next question is we want to sketch tan 3x plus 1. Now if you closely look at, that's related to this question. The reason I did that, because we have the calculations here. Now what we have here is tan 3x plus 1. Now normally the tan 3x, if I get a quick sketch here, I have more room in there. Therefore, I can simply do that. So let's say just there, x and a y. I know this is being squashed by 3 times. Hence, normally the asymptote at pi on 2 and negative pi on 2, my first 2 asymptotes. Now that is divided by 3, so that gives me pi on 6 and negative pi on 6 as the asymptotes. Here I haven't given you any condition for x. Let's say x is between just maybe 2 cycles. Let's try 2 cycles. Well, I'm going to draw the asymptotes first. Now, if I did that, let's say I get my first one here, and then I need to use the rubber to make it a broken line. I know this is at pi on 6 now. Okay, so this is pi on 6. Well, the other one I need to do again onto this side. Let's get this as negative pi on 6. So you can follow me and see whether you get exactly the same answer. Now what you need to remember is, ladies and gents, normally the graph looks like, let me write that, looks like this, isn't it? So that's your tan graph. Now if you look at the graph given, it's in fact not tan 3x, it's plus 1. So what does that mean to us? Okay, the points being shifted up or translated 1 unit up. Well, how do I sketch that then? Okay, so let's sketch that. It's coming up and then again. So that point is 0, 1 now because it has gone up, translated up by 1 unit. The one thing that we must remember is it creates another x-intercept. What could this be? Now if you look at my solutions before, well, it has gone up and now that's our first solution into the left. Now if you look at here, so this is negative pi on 12, 0. I need this point to label on my graph, which means when I sketch this graph, ladies and gents, I need to solve tan 3x equals negative 1. What it means? Well, set y to 0, finding x-intercept. That's what we did before. So finding x-intercepts is quite important in tan graphs here or any other circular functions when you sketch them. Now we found them, therefore we can use it. So that's basically the case. In case if you were to repeat this one for a few cycles, let me get another asymptote here where we are going to repeat this. Let's go down a bit further. Yeah, that's enough, I think. It's vertical enough. And I'm going to treat this as an asymptote. Quickly make it a dotted line. Yeah. Now when I sketch that, you gotta make sure that number, the height at that corresponding points are exactly the same. Now what could that be? So that's pi on 6. Now that's 0. That's again another pi on 6 and another pi on 6, isn't it? So this will be pi on 2. That's 30, 30, 30, altogether 90. This is pi on 3, 60 degrees. Therefore, the point here is pi on 3, 0, but the point there is the next value, which is in fact, just in here if you look at, pi on 4. Therefore, that is pi on 4, 0. So likewise, you need to repeat this graph if you were to, and then also write down or label x and y intercepts. In this case, one y-intercept, and then you get many x-intercepts, depending on how you translate the graph, and also depending on how you reflect. So you got to solve setting y to 0 as you normally do to find x-intercepts. I think it's clear for you now. I would ask you to go and work on the work planner, and I'll catch you again in another video lesson. Bye for now. Thank you.